Studies on process feasibility of using acetylene and diesel as a fuel in CI engines. Abstract necessity for replacement of fuel is growing at a rapid rate since transportation and industry fields are growing widely. Researchers throughout the world are searching for a better alternative than fossil fuels. Acetylene gains advantage over other fuels for its characteristics like high flammability, good calorific value, low cost, and exceptional combustion characteristics. Additionally, acetylene as a fewer carbon content related to supplementary fuels, plays a vital role in environment deprivation. In this paper, an effort has made to check the performance combustion and emission characteristics of CI engine using acetylene as a fuel at various flow rates, 1 lit/min, 2 lit/min, 3 lit/min. The brake thermal efficiency at full load for neat diesel was found to be 34% and for blends it was 33%. For 1 lpm of acetylene, 34.51%, for 2 lpm of acetylene, 35%, for 3 lpm of acetylene fuel consumption decreased by 7.08% for 3 lit/min of acetylene when related with baseline diesel. CO emission was maximum for diesel. The peak pressure is reaching 58.34 bar at full load for baseline diesel. However, the pressure showed increasing trend for acetylene induction. The pressure inside the cylinder after acetylene induction was found to be 62, 66, and 70 bar at full load for 1 lpm, 2 lpm and 3 lpm respectively. Under dual fuel mode at full load, the HRR was found to be 58.34 J/0 Ca, 62.67 J/0 Ca, and 66.12 J/0 Ca, 1 lpm, 2 lpm, and 3 lpm respectively. HRR for baseline diesel under full load was 56.12 J/0 Ca. Results showed a decreased trend in CO emissions for blended acetylene at different flow rates. At full load, NOx emission was maximum for diesel, 1242 ppm. The NOx emissions for blends were 1218, 1239, and 1363 ppm for 1 lpm, 2 lpm, 3 lpm respectively. The maximum HC emission was shown for diesel at full load, and when compared to acetylene at various flow rates showed a decreased trend. Since optimum engine performance has been observed, it can be concluded that acetylene can be successfully used in CI engines as an alternative, and optimal results were obtained for 3 lpm of acetylene injection. 1. Introduction. It has been observed that there is a steep increase in the vehicles and automobile sector. Country's economy is affected due to substantial usage of fossil fuels. The nation's progress depends on how much energy resource is available and how well a country is able to utilize it. The environment pollution from vehicles has big challenge of acid rain and climatic change. Henceforth, governments in the world have been concentrating on utilization of renewable energy resources has to look into environment degradation. Research has been carried out to check the feasibility of alternative fuels in IC engines. This has led to many alternatives like CNG, LPG, methanol, ethanol, acetylene, biodiesel, and biomass resources. The primary requirement of alternative fuel is its availability, cost, and good calorific value. Our study is to check the feasibility acetylene, and it can give better performance on PAR with diesel engine. Research has been carried out using acetylene as a primary fuel and alcohol as a secondary fuel. It was noted that introduction of alcohol reduced the cylinder temperature of the engine. 1. Acetylene has a great potential to substitute fossil fuels. Acetylene with good calorific value and excellent combustion characteristics is definitely a future fuel to look into. Experiments were conducted on SI engine using acetylene as a fuel, and results were tabulated. 2. Nagarajan and Lakshmanan worked on the efficiency and the quality of emission in diesel engine, to inject acetylene at various flow rates. Fixed amount of 3 L/m of acetylene is delivered in dual fuel mode. The outcomes of using diesel as primary fuel under various loads were tabulated. The air-articulated acetylene ended with slight lower efficiency. CO and HC emission reduced considerable when related with baseline diesel. NOx formation significantly increased as acetylene was inducted to the cylinder. 3. Sheikh Kader Basha, P. Srinivasa Rao et al. The tests were conducted with known quantity of acetylene flow rates from 0.1 lit/min to 5 lit/min with an increment of 0.5 lit/min in every step. The primary objective was to find the moderate acetylene flow rate and to reduce emissions. On tabulating the results, the efficiency of acetylene was nearer to diesel with reduction in emissions due to its promising characters. Acetylene is definitely the best alternative with safe operation and slight increase in smoke and NOx. According to Roshan Raman and Naveen Kumar, when they conducted experiments on acetylene at various flow rates of LPM 2, 4, 6, and 8, and compared it with base diesel, they found that optimal results were found for a maximum load of 4 LPM. It was resolved that acetylene can be effectively utilized at 4 LPM. 5. Research has also been conducted by varying the compression ratio, 18, 19, 20, 21, and 22, and flow rate of acetylene of 60, 120, 180 and 240 liters per hour. Optimal results were found at 120 liter per hour and the optimum compression ratio was found to be 21. Hydrocarbon smoke emissions and carbon monoxide were found to be lower with bit increase in NOx emission when related with pure diesel. 6. Deepak Kumar T. and Manjunatha worked on exploration of B20 fish biodiesel in diesel engines blended with waste plastic oil. T was noted that the BTE of blends was 9.5% increased than that of diesel. Due to higher oxygen content in blending mixture led to better combustion of fuel with increased cylinder pressure. HC and CO decreased to certain extent in blends when related with diesel. Conclusion were drawn that plastic oil blended with fish biodiesel can be one of the promising alternate fuel. 7. Renewable energy can be used to major perspective, thereby reducing the usage of fossil fuels. Without any adjustments in CI engine, C2H2 gas was used by parallel production and variable gas flow technique. It was noted that the C2H2 gas was more cost-effective and optimal flow rate was found without compromising on efficiency. 8. Research trend shows that there is enormous scope for emission reduction and cylinder technologies. Developed countries are working upon the technology of using the major energy share with gaseous fuels like acetylene in engines as it is richly available and easily produced. 12. Experiments were done on petrol and diesel engines in dual fuel mode by using acetylene and alcohol. Results reflected that there is a considerable improvement in BTH, and clean burning was noted. Engine life increased when compared with traditional engines. 13. Intensive research was done on acetylene in homogeneous charged compression ignition, HCCI, operating mode. The results stated that NOx and smoke opacity reduced considerable, whereas efficiency was almost same as that of diesel. Most of the researchers have recommended PMI and IJERT technique to reduce NOx emissions when gaseous fuel are used in CI engines. 15. 2. Methodology. Trials were done on a single cylinder, 4-stroke, water-cooled diesel engine Kirloskar make to study the efficiency and emission characteristics of acetylene as a fuel. Figure 1 shows the various parts of the test engine. Eddy current dynamometer was used to control torque and in turn loading on engine. Digital computer synchronized with data acquisition system comprising of sensor was used to know torque, load, speed, fuel intake, and BMEP etc. AVL degas analyzer was used to measure the exhaust gas emissions. Initially the diesel engine was warmed by running it for 20 minutes with diesel. Trials were conducted with increase in torque, loading. The trials were carried out at fixed speed of 1800 rpm by increasing the loads ranging from 0%, 20%, 40%, 60%, 80%, and 100%. Acetylene was injected up to 36% by volume using timed manifold injection, TMI, technique. At 0% loading condition, the flow rate of diesel was found to be 0.78 kg/hr. Diesel flow was reduced upon the induction of acetylene in the range of 1 lt/min, 2 lit/min, 3 lit/min, until the engine attained rated speed of 1800 rpm. The variation of BTE with load for various flow rates of diesel and acetylene is as shown in Fig. 3. The efficiency at full load for neat diesel was found to be 34% and for blends it was 33%. For 1L/m, 34.51%, for 2L/m, 35%, for 3L/m flow of acetylene. The maximum BTE is accounted for 3L/m acetylene injection, 35%. At partial loads with 1L/m of acetylene been injected, the BTE decreases slightly. This may be due to the flame from the ignition center not propagating to entire regions of combustion chamber. With the introduction of acetylene at 3L/m, the BTE increases 35%, due to high flame speed and extensive flammability limits of acetylene. Moreover, acetylene fully participates in combustion, leading to proper mixing and complete combustion of fuel. This displays that there is 1% increase in BTE when related with diesel. It was noted that SFC showed decreased trend with increase in torque. SFC is found to be maximum for diesel, 0.2532 kg/kWhr, and minimum for 3L/m acetylene injection, 0.235 kg/kWhr. So there is 7.18% decrease in SFC of 3L/m acetylene injection. At lower load with slight fuel, heat released is utilized by large air present, which results in low BMEP and high BSFC. At high load, all the air is involved in combustion, which results in increased BMEP and low BSFC. 3.2 Combustion characteristics. Acetylene consists of 2 atoms of carbon and 2 atoms of hydrogen. Moreover, they are bonded by triple bond. When acetylene attains its self-ignition temperature, enormous amount of energy is released due to breakage of triple bond. Acetylene upon reacting with oxygen can reach flame temperature of 30,000 C to 35,000 C, 17, due to breakage of triple bond. Combustion takes place rapidly as acetylene comes in contact with air-fuel mixture, but initially there is a delay in combustion, might be due to presence of acetylene. Diesel fuel is incapable of mixing with air at lower loads. As the load increases, complete combustion of fuel is observed. The deviation of cylinder pressure with combustion process signifies how operative the engine cylinder is. Figure 5 shows the trend of pressure and crank angle. The gaseous fuel is been introduced to cylinder, the pressure increases. This might be due to higher flame speed, more oxygen inside cylinder and higher energy release rate. The peak pressure is reaching 58.34 bar at full load for baseline diesel. However, the pressure showed increasing trend for acetylene induction. The pressure inside the cylinder after acetylene induction was found to be 62, 66, and 70 bar at full load for 1 lpm, 2 lpm and 3 lpm respectively. 3.2.2 Heat released rate. Heat release rate is an important parameter to know how much is the heat released during combustion of acetylene and diesel under dual fuel mode, as it helps to analyze out of total heat release how much quantity of heat was effectively utilized. It has been reported that for diesel operation the burning rate diagram has 4 different phases: ignition delay, premixed combustion phase, mixing controlled combustion phase and late combustion phase. The combustion process in dual fuel mode is also quite similar with 4 different phases: pre-oxidation reaction of gas, combustion of pilot fuel, premixed combustion, and diffusion combustion phase. Figure 6 shows the variation of crank angle and heat release rate. Under dual fuel mode at full load, the HRR was found to be 58.34 J/0 Ca, 62.67 J/0 Ca, and 66.12 J/0 Ca, 1 lpm, 2 lpm, and 3 lpm respectively. HRR for baseline diesel was 56.12 J/0 Ca. When dual fuel mode is compared with baseline diesel, the trend is similar, but a slight variation was observed in pre-mixed phase and diffusion combustion phase. This is due to less pre-mixed combustion of diesel with inducted acetylene and also due to the presence of unburned acetylene. 3.3.2 Nitrogen oxides. Fig 7 depicts the deviation of CO emissions with load. The emission of CO results from improper combustion of HC. The formation of CO can be avoided by enriching the oxygen in the fuel. Due to combustion there is a steep increase in pressure and temperature at higher loads resulting in complete combustion leading to low CO formation. Air-fuel ratio is also the primary factor in accessing the formation of CO. Better air-fuel mixing tends to complete combustion which further leads to less CO formation. For baseline diesel at full load CO was found to be 0.045%, whereas after induction of acetylene the CO level reduced to 0.040%, 0.038% and 0.035% for 1 lpm, 2 lpm, and 3 lpm respectively. CO reduces by 22.33% for 3 lpm acetylene induction compared to diesel. NOx emissions such as nitrogen monoxide and nitrogen dioxide are harmful to mankind. Fig 8 depicts the deviations of NOx emission related to load. Higher temperature is more suitable for NOx formation. NOx emission increases with the temperature raise. It is noted from the figure that as the torque, load, increase the NOx emissions increase. This is because as diesel engines have higher compression ratio, which in turn leads to peak temperature making way for the formation of NOx. NOx formation is in turn dependent on temperature. The maximum NOx emissions at full load were showed for diesel, 1242 ppm. The NOx emissions for blends were 1218, 1239, and 1363 ppm for 1 lpm, 2 lpm, 3 lpm respectively. The trend of NOx at baseline diesel with 1 lpm and 2 lpm, acetylene induction showed similar trend. However, NOx increased by 4.6% for 3 lpm of acetylene induction. This might be due to higher flame speed, excess air causing high cylinder pressure and temperature. Hydrocarbons are organic-based compounds. Hydrocarbons are formed due to incomplete combustion of fuel. Fig 9 depicts the deviations of HC emission related to load. At full load HC emission for diesel was 104 ppm. The HC emissions for blends were found to be 100,97,94 ppm, for 1L/m, 2L/m, 3L/m of acetylene injection, which is 9.6% lower than that of diesel. This may be due to higher burning velocity of acetylene and due to too much of air and less quantity of fuel in engine. 4 conclusions. In this study, experimental analysis was done to check the performance, combustion and emission characteristics of CI engine using acetylene as a fuel at different flow rates, 1 lit/min, 2 lit/min, 3 lit/min. Trials were carried out under same condition and repeated 3 times to obtain steady values. The brake thermal efficiency at full load for neat diesel was found to be 34% and for blends it was 33%, for 1L/m of acetylene, 34.51%, for 2L/m of acetylene, 35%, for 3L/m of acetylene. Fuel consumption decreased by 7.08% for 3 lit/min of acetylene when compared with baseline diesel. The peak pressure is reaching 58.34 bar at full load for baseline diesel. However, the pressure showed increasing trend for acetylene induction. The pressure inside the cylinder after acetylene induction was found to be 62, 66, and 70 bar at full load for 1 lpm, 2 lpm and 3 lpm respectively. Under dual fuel mode at full load the HRR was found to be 58.34 J/0 Ca, 62.67 J/0 Ca, and 66.12 J/0 Ca, 1 lpm, 2 lpm, and 3 lpm respectively. HRR for baseline diesel under full load was 56.12 J/0 Ca. At full load maximum NOx emission were showed for diesel, 1242 ppm. The NOx emissions for blends were 1218, 1239, and 1363 ppm for 1 lpm, 2 lpm, 3 lpm respectively. The CO emission was maximum for diesel. It clearly showed a decreased trend in CO emissions for blended acetylene at different flow rates. HC emissions at full load are observed for diesel, 104 ppm. The HC emissions for blends were found to be 102, 98, 97 for 1L/m, 2L/m, 3L/m of acetylene injection. Since optimum engine performance has been observed, it can be concluded that acetylene can be successfully used in CI engines as an alternative, and optimal results were obtained for 3 lpm of acetylene injection.